To steal a part of a production language model. Like when a large language model is productionized, and if you are given an API access, can you steal part of the source of the large language model? And the answer is yes. And this is the paper, one of the craziest papers that I've read in the recent times, to be really honest. It took me a lot of time to understand this paper. This is a paper that was put out by a very crazy group, Google DeepMind, ETH Zurich, University of Washington, OpenAI, and McGill University. So what they're trying to prove in this paper is that when you have a large language model, not the weights, not the source code, but when you have an API access to a large language model, can you guess non-trivial information from that? Typically, a deep learning model or a deep neural network is considered to be a black box model. To understand what goes inside it is not very easy, and it is something that people are still trying to understand. And in this situation, even if you do not have access to the model, can you guess? Can you guess precisely? Can you extract non-trivial information from that API, whatever that information is from that model? That is exactly what this paper is saying. We introduced the first model stealing attack that extracts precise non-trivial information from black box production language models like OpenAI's ChatGPT. No joke, actually they did it with OpenAI ChatGPT or Google's Palm 2. Specifically, our attack recovers the embedding projection layer up to symmetries of a transformer model. We'll come to that. What does it mean later? Given typical API access, all you need is API access. For under $20, our attack extracts the entire projection matrix of OpenAI's Ada and Babbage language models. These are like the smaller size models that were like heavily used for embeddings and all the other things in the early days of OpenAI. We thereby confirm for the first time that these black box models have a hidden dimension of 1024 and 2048 respectively. So this is the dimension information that they have extracted. We also recover the exact hidden dimension size of GPT 3.5 Turbo, one of the most popular and also not open model. And they have extracted the exact hidden dimension size of GPT 3.5 Turbo and estimate that it would cost under 2000 queries. Like all you need is like less than $2,000 in queries to recover the entire projection matrix. We conclude with potential defenses, mitigations, and discuss the implications of possible future work that could extend our attack. Now, what is it? It's super impressive. It's honestly like very impressive. But what does it mean? Let's take a quick look at a very small part of a large language model, or let's say transformers. You all know that transformers do one thing, which is next word prediction. Or I should say that the large language models based on transformers do next word prediction. So when you have given an input, let's say the cat sits on the, then it actually gives you that the mat, that is the response that it gives you. So this is the input that you give and this is the output the model is actually trying to predict, or the model is going to give you. But before that happens, this is the final projection layer. But before that happens, there is a hidden layer. OpenAI doesn't tell what is in the hidden layer. OpenAI doesn't tell the dimension of the hidden layer. And all you know is at the end of the day, this particular word mat. And there is one more extra information that you can know. It's called log probs. It's called log probs. What is log probs? When it is going to predict something. For example, for this particular passage, the large language model predicted the final word. Here is hi. But before it did that, there are more words. This is defined by top k. There is a value called top k. And this is like it samples from a list and then it gives you the log probs, the log probability of these 5 words, the top 5 words. The probability of hi is 97.58. The probability of mod is 2.38. The probability of hi with high uppercase H is 0.04 and so on. So now what the researchers here have done is that one, they have tried to use this particular feature, which is log probs, to get the entire weight of the matrix, which is this matrix, The two, they just wanted to simply show that we can predict, or we can guess precisely the dimension of the hidden layer, which is not visible, or which is not companies usually share. So these are the two things that they're doing. One, give you the dimension so that you know what is the dimension of this embedding projection layer, which is one side is the hidden layer, the other side is what the projection layer is. And the second, they also try to use this log probes and try to actually build the entire matrix, not just the dimension, but entire matrix. These are the two things that these researchers have tried to do. I mean, this is my simplification or oversimplification of explaining what they're doing here. So the contributions of this paper, we introduce an attack that can be applied to black box language models and allows us to recover the complete embedding projection layer of a transformer language model. Our attack departs from the prior approaches that reconstructs a model in a bottom-up fashion, starting from the input layer. Instead, our attack operates top-down. So if you consider this to be the top part of the model, then their attack starts from here rather than the bottom-up approach, however direction you want to call it. So instead of starting from the input layer, they're starting from the output layer, the last layer, and directly extracts the model's last layer. Specifically, we exploit the fact that the final layer of a language model projects from the hidden dimension to a higher dimensional logit vector. As you can see here, this is a lower dimension. So this is a higher dimension. As you can see here, the hidden layer, it projects up to a higher dimension layer. So that's what they're saying here, that specifically we exploit the fact that the final layer of a language model projects from a hidden dimension to a higher dimension logit vector. Logit vector, higher dimension, the hidden dimension, the lower vector or smaller dimension. This final layer is thus low rank, and by making targeted queries to the model's API, all they're doing is using API, we can extract its embedding dimension or its final weight matrix. So one, they can get the embedding dimension. Second, they can get the final weight matrix, which is they have to use the log probes. Stealing this layer is useful. Now you might be wondering, hey, let's take a break and understand what is the use of doing this. If you're going to steal here, what is the use? First, it reveals the width of the transformer model, which is often correlated with its total parameter count. So if you want to know the total parameter count, and if an LLM provider has not given you, in many cases you don't get to know, like if it's a closed model, they're saying that this can give it, like this is highly correlated and can give you. Second, it slightly reduces the degree to which the model is a complete black box model. As I mentioned at the start of the video, deep learning models are complete black box. So anytime you can open the black box even a little bit, it helps people in research and understanding what is happening, which so might be useful for future attacks. Third, while our attack recovers only a relatively small part of the entire model, the fact that this is possible to steal any parameters of a prediction model is surprising and raises concern that extensions of this attack might be able to recover more information. And finally, very finally, recovering the model's last layer and thus the hidden dimension may reveal more global information about the model, such as relative size differences between different models. Our attack is effective and efficient and is applicable to prediction models. It has to be productionized, like it has to be available somewhere, whose APIs expose full log probes or logit bias. And this included Google's Palm 2 and OpenAI's GPT-4, and it gives you more details. And also now, if you think that, hey, they hacked into OpenAI, which is very bad, they shouldn't have done it, they're hackers. I mean, if you're in that school of thought, they have said that they have done responsible disclosure. We have received approval from OpenAI prior to extracting the parameters of the last layer of their models, worked with OpenAI to confirm our approach's efficacy, and then deleted all data associated with the attack. And in fact, after this, OpenAI and Google have both modified their APIs to introduce mitigation and self-defense to make it more difficult for adversaries to perform this attack. Okay, Now let's get into the detail of what this attack is. Once again, I'm going to do my best to explain what is happening here. So what is happening here is, let's say that you have got a model, the model API, and for some reason they decided to call it Oracle. So let's call it Oracle. So you have got a model or an interface that is something that you can use. So O, or whatever this is a perfect Oracle. So if you give an input sequence P, it produces an output, which is Y is O of P. That is exactly what is happening here. What is happening here? You give an input, right? And you get an output Y. So this is your P, the input sequence here that you give. And this is your output, which is Y. This is without leaking any information about the function. So this is what you're getting. Now what they're trying to do here is, they're trying to say that if whatever you're getting as an output is actually a sampled from a probability distribution, right? So there is a vocabulary and everything that you get as an output. So we study the models that take a sequence of tokens drawn from a vocabulary as input. Let P of X denote the space of the probability distributions over X. So everything here is a probability distribution. We study parameterized models, function theta, xn, P of X, that produce a probability distribution over the next output token, given an input sequence of n tokens. So if you give an input sequence of n tokens, it goes to the probability distribution, it samples from that, and the things that has got the tokens that has got the highest probability score, it gives you an output. And that is what this is. And that is what they're doing. So now you have got a matrix L into H. H is the hidden layer and L is the logit one. So you have got L, which is the logit one, the logit vector, and H is the hidden layer, which is what we are ultimately trying to figure out. So everything here is part of this. Note that the hidden dimension size is much smaller than the size of the token dictionary. So as you can see, the token dictionary could be long, like the vocabulary, and the hidden layer is small, that is small. So H is much smaller than L. This is like a very well-known fact in the deep learning world. So you compress the knowledge, you take it, and then you project it to a higher layer, and that's how you get the output. For example, llama chooses H, a subset of this, and L is equal to 32,000. So H is one of this, right? But the L, the logit is 32,000. So the vocabulary size here is like around 32,000. So there is a recent trend towards increasingly large token size. GPT-4 has got approximately 100,000 token vocabulary. We in fact saw Google's recent model Gemma also had really high vocabulary, and that is exactly why Gemma is an ideal candidate for you to fine tune it for your own languages and all these things. Now I'm digressing. So what they're doing, the algorithm is actually like very simple if you see. Now you have got the Oracle LLM O. So first one is hidden dimension extraction. All we are going to extract is the dimension. Even I'm not going to explain how they're going to do the metrics. If you know, if you understand it well, please let me know in the comment section. First, they have the Oracle LLM O, or whatever that symbol is. So you have an initialize n value. So take a random n value to an appropriate value greater than h. So you guess what h could be, and then you take a value that is greater than h, or you believe that is greater than h. And then you initialize an empty matrix. It has nothing. It has n by l. What we are trying to do? We are trying to figure out h by l. For iteration, now you're going to do the iteration. I is equal to 1 to n. So whatever that n is, you're going to randomly choose a prompt and then send it, get the output and put it in the matrix. That's all you're going to do. And you're going to repeat it, and you're going to repeat it, you're going to repeat it. For example, let's say we have initialized n as 2048. Then you're going to do this from 1 to 2048, and every single prompt you're going to get it and put the weights back. And then you're going to use a technique called SVD. I think it stands for singular value decomposition, if I'm not wrong. Either single value decomposition, if I'm not wrong. SVD is a very popular technique that people have been using, or at least like before deep learning, people have used SVD to reduce dimensions for a lot of different purposes. So they're going to use SVD and then finally get the count, and that is how you're going to get h by l. That's the end. So intuition. I'm going to explain the same thing without the algorithm part. Suppose we query a language model on a large number of different random prefixes. Even though each output logic vector is an L dimensional vector, they all actually lie in a H dimensional subspace because the embedding projection layer up projects from H dimensions. So this output is one word, but when you get it like this becomes a logic vector. And the logic vector, even though it comes from this layer, the projection layer, it is actually coming from the hidden layer, which is much smaller. So the hidden layer up projects it up to the projection layer, which is like larger in size. So that's what they say here. Even though each output logic vector is an L dimensional vector, they all actually lie in H dimensional subspace. So we know H is smaller, L is bigger, because the embedding projection layer up projects from H dimensions. Therefore, by querying the model NF, which is in this case, what do they mean by NF? Is more than H times. If H is 2048, then you have to query more than 2048. If H is 1024, then you have to query more than 1024. We will eventually observe new queries are linearly dependent on past queries. So you know this can have like, let's say, only 1024. So by querying this again and again and again more than 1024, you will start seeing some pattern, a linear pattern before something that you have already queried, because that's where it comes from. So somehow you should be able to figure it out. So we can then compute the dimensionality of this subspace, this subspace with SVD, singular or single values decomposition, and report this as the hidden dimensionality of the model. And this is the idea. I've tried my best to explain. Let me know in the comment section if it makes sense. This is the example of how it happens. They've taken a model called Pythia and they've queried again and again and again. So 1024 queries, this blue line, 1536 queries. This is the green color is 2048 queries. And you can see suddenly beyond 2048, you can start seeing things going a little haywire. So you can see the red color line 2560 just coming here and suddenly dripping and then coming down. And then 3072 suddenly coming here and dripping. Why? The primary reason is because the model does not have any new information. So what is happening here? In order to visualize the intuition behind this attack, figure 1 illustrates an attack against the Pythia 1.4. It's a 1.4 billion LLM. Here we plot the magnitude of the singular values of Q as we send an increasing number of queries to the model. So this is the magnitude of Q and the output matrix, and this is the number of times they are actually sending. When we send fewer than 2048 queries, anything that is lesser than 2048, we can actually see it is impossible to identify the dimensionality of the hidden space, because it's obvious. This is because n is less than h. What is the h here? The right answer here is 2048. Because n is less than h, and so n by L dimensional matrix Q has full rank and n non-trivial singular values. But once we start making more than 2048 queries to the model, thus n becomes greater than h. So h is the limit, n becomes greater than h. The number of numerically significant singular values does not increase further. So SVD is compressing things for you. So after 2048, the values do not increase significantly. And because of that, you see this drop. And that is when you understand, okay, this is the point where there is h. So you use n, go one by one, one by one, one by one. And the point where you don't see a significant increase, you understand I've milked everything from the hidden layer. I don't have anything more to milk from the hidden layer. And that's why it does not increase significantly. And that is what SVD tells me. So this is the point as the value of the h. And if you see the second plot, it might become much easier. In the figure 2, we plot differences in the log space between subsequent singular values. As we can see, the largest difference occurs at almost exactly 2048 singular value, the true hidden dimensionality of the model. You can see here the difference. It just like increases, changes, and suddenly drops. And then it just like changes. It doesn't go back to the same state. And the reason is because you don't have any significant increase in new information. So the SVD starts compressing it. And that's something that you can see here also. What they call it as stolen size is what they're extracting from this. For GPT-2, the hidden dimension, the actual value is 768 and the stolen size is 757. Their approach has given you 757. This is the RMS, like the error metric. GPT-2 XL, they can see the actual value is 1600 and their model said 1599 plus or minus 1, and it goes on, and they're almost pretty good with a lot of this. Llama 7 billion model, 65 billion model, they've done a pretty good job. And you can see for larger models, the error has actually gone down. And this is what they have done. And they have done the same thing, but with more information, with more like the top K value and all the other things. And using the logit, they are also populating the entire weight matrix. So here we saw that they're just getting the information, right? The dimensions. But next step, they're going to get the entire matrix itself, which they're going to do with the second attack. So the result of this attack, I think this video is already going to be very longer and confusing. So I'm going to stop very soon. So the result of this entire paper is this. They've got 1, 2, 3, 4, 5 models, and with OpenAI especially. And we know the size of this, 1024, they revealed it. Babbage 2048, Babbage 002, 1536, that's a very weird sizing. OpenAI GPT 3.5 Turbo Instruct and the other model, OpenAI told them not to release the information. And they respected it. Cool. So the number of queries that they had to use, because they have to iteratively get it again and again and again. And the cost is $1 and it goes up till $800. And the RMS also, if you see for the weight matrix extraction, the number of queries, and it goes. So this is just for the dimensions, from $1 to $800 for dimensions, and from $4 to $8,000 for weight matrix extraction. So if you can see that from $1 to $8,000, you can both extract the dimension of the hidden layer or the hidden embedding projection layer, and also you can extract the weight matrix. So we don't know exactly how good the weight matrix is, like they started hiding the RMS value, but you can understand that this is pretty interesting. Like the fact that you can go to an API and extract from the API what is part of the original model. I think this is mind blowing. It's almost like if you are a food scientist or food tester, from the made up food, like the cooked up food, you try to understand the ingredients. That's quite easy with the food because you see the food. Here you don't see anything. I think this is pretty remarkable research. Let me know in the comment section what do you feel. Also, let me know like if it made sense. Like it was like it took a lot of time for me to comprehend and then create a story around it. Let me know in the comment section. See you in another video. Happy prompting.